Tonight, we journey towards something that will change how you think about scale, about distance, about everything you believed made something truly large. We are going to discover the biggest object ever found in the universe. And I should tell you now, when this is over, the night sky will look different to you. You will grasp something most people never consider, something that makes entire galaxies appear like tiny grains of dust. If you find value in these deep journeys into space, think about subscribing or leaving a like. It genuinely supports the channel and lets me continue creating videos like this one. Let us start with something you know well: your home. The typical house in America measures around 2,500 square feet. That is a space you could cross on foot in roughly 30 seconds. You understand every part of it. This is a scale your mind can easily process because you live it each day. Your brain developed to comprehend spaces like this, places you can observe, places you can move through. Think about how you navigate your home in the dark. You know where the furniture sits. You know how many steps lead from your bedroom to the kitchen. Your brain has mapped this space completely. This intimate knowledge comes from direct experience, from thousands of journeys through the same rooms. Your senses evolved to handle spaces exactly this size. You can judge distances with your eyes, hear sounds reflecting off nearby walls, reach out and touch objects within arm's length. This is the scale of human existence. Your brain contains specialized neurons that create an internal map of familiar spaces. These place cells and grid cells fire in specific patterns as you move through your environment, building a cognitive representation of where things are. This neural architecture evolved over millions of years, optimized for navigating territories measured in miles, not light years. Our ancestors needed to remember where food sources were, where dangers lurked, where shelter could be found. They did not need to comprehend distances measured in billions of light years. This is why astronomical scales feel so alien. Your brain has no direct experience with them. When we talk about a structure 1 billion light years across, these are not numbers your intuition can grasp. We must build understanding slowly, step by step, using comparisons and analogies. We must translate the incomprehensible into terms that connect to your lived experience. A football field, when you include both end zones, stretches 360 feet long. You could walk from one goal line to the other in perhaps 2 minutes. A mile equals 5,280 feet, roughly 17.5 football fields, placed end to end. Most people can cover a mile on foot in around 15 to 20 minutes. These are distances that seem significant yet reachable. You might walk a mile to a nearby store or run several miles for exercise. These distances require effort, but they remain comprehensible. You can picture them in your mind. Consider a marathon, 26.2 miles. Elite runners complete this distance in just over 2 hours. For most people, it might take 4 or 5 hours of continuous movement. This represents the outer limit of distances humans routinely travel under their own power. Beyond this, we rely on vehicles, on technology to extend our reach. The span from New York to Los Angeles measures about 2,800 miles. That is a 5-hour flight, or roughly 40 hours of driving if you somehow never paused. Most people who make this journey do so by air, watching the landscape scroll beneath them, seeing the transition from eastern forests to midwestern plains to western mountains to Pacific coast. The journey is long enough to require planning, yet short enough to complete in a single day of travel. If you drove this distance at 60 miles per hour without stopping, you would pass through roughly a dozen states. You would cross the Mississippi River, traverse the Great Plains, climb over the Rocky Mountains, descend into deserts, and finally reach the Pacific Ocean. The journey encompasses an enormous diversity of landscapes, climates and ecosystems. And yet, in cosmic terms, this is an invisibly small distance. The distance around Earth at the equator comes to about 24,901 miles. If you could circle the entire planet without stopping at typical highway speeds, it would require about 383 hours, nearly 16 days of non-stop driving. This is a distance that pushes the limits of human travel. No one has ever driven around Earth without stopping. The journey would span multiple continents, cross oceans by ship or bridge, pass through dozens of countries and climate zones. And yet, Earth is a single object, a sphere you could theoretically circle if given enough time. The deepest humans have ever travelled into Earth is about 7.5 miles in a mine in South Africa. The deepest point in the ocean, the Mariana Trench, lies nearly 7 miles below the surface. Earth's diameter is roughly 7,900 miles. We have barely scratched the surface of our own planet. The vast majority of Earth's interior remains unexplored, unreachable with current technology. But here is what matters. When compared to the scale of our solar system, Earth is minuscule, and when compared to the scale of our galaxy, the solar system is minuscule. And when compared to the largest structures we have found, our galaxy is minuscule. We are about to ascend a ladder of scales, each step making the one before it seem microscopic. The Moon sits roughly 238,855 miles from Earth. When the Apollo astronauts journeyed to the Moon, they travelled farther than any human had ventured before. The trip required about 3 days at speeds near 24,000 miles per hour. The fastest you have likely ever moved is in an aircraft, perhaps 500 miles per hour. The Apollo spacecraft moved nearly 50 times faster than that, and the journey still took 3 days to reach the Moon. Imagine watching Earth shrink behind you on that journey. For the first few hours, Earth would fill the window, a massive sphere of blue and white. Gradually, it would diminish, becoming smaller and smaller until it could be blocked by your thumb held at arm's length. The astronauts reported a profound shift in perspective. For the first time in history, humans saw their home planet as a complete sphere floating in darkness, a fragile oasis in the void. The Moon itself is about 2,100 miles in diameter, roughly 1/4 the size of Earth. Its surface area equals about the combined land area of Africa and Asia. When humans first stepped onto the lunar surface in 1969, they left footprints that remain there today. With no atmosphere, no wind, no water, nothing disturbs the lunar dust. Those footprints will persist for millions of years, silent testament to humanity's first journey beyond Earth. The distance to our Sun places all of this in a new light. Our Sun lies about 93 million miles from Earth. If you could somehow drive there at highway speeds, 65 miles per hour, without stopping, it would require about 163 years. You would need to hand the wheel to your children, who would pass it to their children, who would pass it to their children, and somewhere around your great-great-great-grandchildren, the vehicle might finally reach its destination. This distance, the gap between Earth and Sun, defines what astronomers call an astronomical unit. It serves as a convenient yardstick for measuring distances within our solar system. The planet Mercury orbits at about 0.4 astronomical units from the Sun. Venus orbits at about 0.7 astronomical units. Mars orbits at about 1.5 astronomical units. These inner planets cluster relatively close to the Sun. The outer planets lie much farther out. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units from the Sun. Its distance from the Sun is more than 5 times Earth's distance. Saturn, with its magnificent rings, orbits at about 9.5 astronomical units. Uranus lies at 19 astronomical units. Neptune, the most distant major planet, orbits at roughly 30 astronomical units from the Sun. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending to about 50 astronomical units. Small worlds like Pluto orbit here, remnants from the formation of the solar system. Even farther out, the Oort cloud, a vast sphere of comets, may extend to 100,000 astronomical units from the Sun, halfway to the nearest star. Light moves at about 186,282 miles per second. Every single second, light covers 186,282 miles. When you turn on a lamp, the light reaches your eyes almost immediately because the distance is so brief. But when you observe our Sun, you are seeing light that departed its surface roughly 8 minutes and 20 seconds ago. If something occurred on the surface of our Sun right at this moment, we would not learn about it for more than 8 minutes. This creates a strange situation. We never see the Sun as it is right now. We always see it as it was 8 minutes ago. If the Sun suddenly vanished, impossible though that is, we would continue to see it for 8 more minutes, and we would continue to feel its warmth and gravity. Then, all at once, the light would disappear, the warmth would begin to fade, and Earth would start drifting away on a straight line through space. The Sun's gravity, like its light, takes 8 minutes to reach us. Light from Mercury takes about 3 minutes to reach Earth. Light from Venus takes about 2.5 minutes. Light from Mars, depending on where it is in its orbit, takes between 4 and 21 minutes. Light from Jupiter takes between 32 and 52 minutes. Light from Saturn takes over an hour. Light from Neptune takes more than 4 hours to reach us. This means when we observe the outer planets through telescopes, we see them as they were hours ago. Any changes in their atmospheres, any new storms or features, take hours to become visible to us. We observe the solar system not in real time, but with a delay that increases with distance. Because of these immense distances, astronomers rely on a measurement called the light year. Despite containing the word year, a light year is not a unit of time, it is a unit of distance. It represents the distance that light travels in 1 year. Here is how it works. Light travels 186,282 miles every second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. When we multiply these numbers together, we arrive at approximately 5.88 trillion miles. Try to picture a trillion miles. It is a number so large it loses meaning. If you counted to 1 trillion at a rate of 1 number per second, never stopping to sleep or eat, it would take you more than 31,000 years. A trillion miles is roughly the distance light travels in about 2 months, and a light year is 6 times larger than that. To put this in perspective, the entire solar system, from the Sun to the outer edge of the Oort cloud, spans about 2 light years. The distance from Earth to Neptune is less than 1/10,000th of a light year. The distances we just discussed, which seemed so enormous, are tiny fractions of a light year. The closest star to our solar system, aside from our own Sun, is called Proxima Centauri. It is a small red dwarf star located about 4.24 light years away. That means the light you observe from Proxima Centauri tonight departed that star more than 4 years ago. It has been crossing through the emptiness of space for over 4 years, travelling nearly 25 trillion miles to arrive at your eye tonight. Proxima Centauri is part of a triple star system called Alpha Centauri. The 3 stars orbit each other in a complex gravitational dance. The two brighter stars, Alpha Centauri A and Alpha Centauri B, orbit each other at a distance similar to the distance between the Sun and Uranus. They complete one orbit every 80 years. Proxima Centauri orbits this pair at a much greater distance, taking perhaps 500,000 years to complete one orbit. From our perspective, they appear as a single bright point in the southern night sky. Alpha Centauri is the third brightest star visible from Earth, a prominent beacon in the constellation Centaurus. But Proxima Centauri itself is too dim to see with the naked eye, despite being our nearest stellar neighbour. You would need a telescope to spot it, a faint red ember beside its brighter companions. Recent observations have revealed that Proxima Centauri hosts at least 2 planets. Proxima Centauri B orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. This discovery has fueled speculation about the possibility of life on the nearest exoplanet to Earth. However, red dwarf stars like Proxima Centauri are known for violent flares that could strip away planetary atmospheres, making life challenging. If we could travel at the speed of the Apollo spacecraft, about 24,000 miles per hour, reaching Proxima Centauri would take roughly 120,000 years. That is longer than modern humans have existed on Earth. We would need to build a generation ship, a vessel designed to support many generations of people during the journey. The people who arrived would be the distant descendants of those who departed, connected to them by thousands of generations born and raised in space. Even communicating across this distance presents challenges. If we sent a radio message to Proxima Centauri today, it would take 4.24 years to arrive. Any reply would take another 4.24 years to reach us. A simple exchange, question and answer, would require 8.5 years. A conversation would be impossible. Interstellar communication means sending messages to the future and receiving replies from the past. Within roughly 16 light years of our solar system, there exist approximately 50 stellar systems. This region of space, this sphere, about 32 light years across, forms our local stellar neighbourhood, and in cosmic terms, it is incredibly small. Most of these nearby stars are red dwarfs, small, cool stars that burn their fuel slowly and can live for trillions of years. A few are stars similar to our Sun. A couple are white dwarfs, the dense remnants of stars that have already died. Together, they form the immediate neighbourhood around our Sun. Many of these stars have planets. As telescope technology improves, we discover more exoplanets orbiting nearby stars. Some are gas giants larger than Jupiter. Some are rocky worlds similar to Earth. Some orbit in their star's habitable zone. The nearest stars represent our best opportunity for detailed study of other planetary systems and, potentially, for finding signs of life beyond Earth. The Milky Way galaxy, our home galaxy, measures roughly 100,000 light-years across. The galaxy is approximately 23,500 times wider than the distance to our nearest stellar neighbour. And our galaxy holds somewhere between 100 billion and 400 billion stars. Each of those stars resembles our own Sun, a massive sphere of hydrogen undergoing nuclear fusion, potentially accompanied by its own collection of planets circling around it. Think about that number for a moment. 100 billion stars at minimum. If you tried to count them at 1 star per second, it would take you more than 3,000 years. And each star is a sun, potentially with worlds of its own. Some of those worlds might have oceans, atmospheres, weather systems. Some might harbour life. The sheer abundance of possibilities within our galaxy alone is staggering. The Milky Way is a spiral galaxy. It has a bright central bulge surrounded by a flat disk containing several spiral arms. These arms are not permanent structures. They rotate around the galactic center, though not like a solid wheel. Different parts of the galaxy rotate at different speeds, causing the spiral pattern. The arms are regions where stars form more actively, lit up by young, hot, blue stars and glowing clouds of gas. The spiral arms have names. We reside in the Orion Arm, also called the Orion Spur, a minor arm between two major arms. The Perseus Arm lies farther from the galactic center, while the Sagittarius Arm lies closer. These arms are vast structures, thousands of light years wide and tens of thousands of light years long. They trace out the overall shape of our galaxy, a magnificent pinwheel slowly rotating in space. At the center of the Milky Way lies a supermassive black hole called Sagittarius A star. It contains about 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. This black hole is currently quiet, not actively consuming large amounts of matter, but observations reveal stars orbiting it at tremendous speeds, whipping around the galactic center in elliptical paths. These observations provide some of the best evidence we have for the existence of supermassive black holes. Our solar system resides about 26,000 light-years from the center of the Milky Way. We occupy one of the spiral arms. When you gaze upward at the night sky and notice that faint ribbon of light stretching across the darkness, you are observing the disk of our galaxy seen edge-on. You are witnessing hundreds of billions of stars so far away that their individual lights merge together into a continuous glow. On a clear night far from city lights, the Milky Way appears as a glowing band stretching from horizon to horizon. Ancient cultures saw it as a river, a path, or a bridge. The ancient Greeks called it the Milky Circle, believing it was milk spilled by the goddess Hera. The Romans called it the Via Lactea, the Milky Way. In Japanese mythology, it is the river of heaven, separating two lovers who can meet only once a year. In Hindu mythology, it is the path of Aryaman. In Norse mythology, it is the path souls take to Valhalla. Every culture that looked up at the stars noticed this band of light and wove it into their stories. The Sun, at the heart of our solar system, orbits the center of the Milky Way at a velocity of about 515,000 miles per hour. But the galaxy is so enormous that even at this velocity, it requires about 225 to 250 million years to complete a single orbit. The last time our solar system occupied its current position in the galaxy, dinosaurs had not yet evolved. The Earth existed in the Triassic period. Since that time, dinosaurs evolved, ruled the planet for over 160 million years, became extinct, mammals rose to prominence, primates developed, humans emerged, constructed civilizations, created technology, and looked up at the stars. And we have only just now finished one lap around the galaxy. This orbital period has been called a cosmic year or a galactic year. During each cosmic year, our solar system makes a complete circuit around the galaxy, passing through different regions of space, encountering different stellar neighbors, moving through spiral arms and the voids between them. As we orbit, we pass through regions of higher and lower stellar density, regions with more or less gas and dust. Some scientists have speculated that these passages might influence Earth's climate or even trigger mass extinctions, though the evidence remains uncertain. The Earth has completed about 20 cosmic years since it formed 4.5 billion years ago. During those 20 revolutions, life emerged, evolved from single cells to complex multicellular organisms, colonized the land, developed consciousness, and began contemplating the cosmos. All of Earth's history compressed into 20 laps around the galaxy. Now, the Milky Way is not isolated. The Milky Way belongs to a collection of galaxies called the Local Group. The Local Group includes more than 80 known galaxies. The three largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The rest are mostly small dwarf galaxies, some containing only a few million stars, orbiting around the larger galaxies like moons around planets. Dwarf galaxies are the most common type of galaxy in the universe. They contain far fewer stars than giant galaxies like the Milky Way, sometimes as few as several thousand stars. Many orbit larger galaxies, gradually being pulled apart by tidal forces over billions of years. Their stars get stripped away, joining the halo of the larger galaxy. This process, called galactic cannibalism, is how large galaxies like the Milky Way grow over time. Some of these dwarf galaxies are satellites of the Milky Way. The Large Magellanic Cloud and the Small Magellanic Cloud are the two largest. They orbit our galaxy at distances of about 160,000 and 200,000 light-years respectively. From the southern hemisphere, they appear as faint, cloudy patches in the night sky, like pieces of the Milky Way that have broken off. They are actually separate galaxies, each containing billions of stars. The Large Magellanic Cloud is particularly interesting. It contains active star formation regions, including the Tarantula Nebula, one of the largest and most active star-forming regions known. Massive young stars illuminate vast clouds of gas, creating spectacular views through telescopes. The Small Magellanic Cloud is more disrupted, pulled into an elongated shape by the Milky Way's gravity. Other satellite galaxies are much smaller and dimmer. The Sagittarius Dwarf Elliptical Galaxy is currently passing through the disk of the Milky Way, being torn apart in the process. Streams of its stars trail across the sky, evidence of its disruption. The Canis Major Dwarf Galaxy lies even closer, discovered only in 2003. It too is being consumed by the Milky Way, its stars joining our galaxy's outer regions. The Andromeda Galaxy sits about 2.537 million light-years away. When you look at Andromeda in the night sky, and you can spot it with your unaided eye if you know its location, you are observing light that left that galaxy over 2.5 million years ago. When that light started its journey toward your eye, our ancestors had not yet evolved. Everything you understand about human civilization has unfolded while that light was crossing space toward you. Andromeda appears as a faint smudge in the constellation Andromeda, visible on autumn evenings in the northern hemisphere. Through a telescope, you can see its spiral structure, its bright central bulge, its graceful arms. Through large telescopes, you can resolve individual stars in Andromeda's outer regions. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars. It stretches about 220,000 light-years across, more than twice the diameter of our galaxy. Andromeda is rushing toward us at about 70 miles per second. In about 4 billion years, the two galaxies will collide and merge, creating a giant elliptical galaxy. Astronomers have already named this future galaxy Milkomeda, but this collision will be gentle on stellar scales. The stars themselves are so far apart that they will pass through each other like two swarms of bees. Very few, if any, actual stellar collisions will occur. However, the gravitational interactions will be dramatic. Both galaxies will be severely disrupted. The disk structures will be destroyed, stars flung into new orbits. Some stars will be ejected entirely, becoming intergalactic wanderers. The gas clouds in both galaxies will collide, triggering enormous bursts of star formation. The night sky from Earth, if Earth still exists, will be spectacular, filled with new stars and illuminated by colliding gas clouds. The supermassive black holes at the centers of both galaxies will spiral together and merge, creating an even more massive black hole. This merger will release gravitational waves, ripples in space-time that will propagate across the universe. By that time, our sun will have swollen into a red giant, possibly engulfing Earth. Any descendants of humanity will have long since left Earth or gone extinct. The Triangulum Galaxy, the third largest in the local group, lies about 3 million light-years away. It contains perhaps 40 billion stars, making it the smallest of the three major galaxies. It too is approaching the Milky Way and Andromeda, and will likely merge with them in the distant future. The final result will be a single, massive elliptical galaxy containing all the stars from what are now three separate galaxies. The local group measures about 10 million light-years across. That is 100 times the diameter of the Milky Way. And yet, in the larger picture, the local group is a small structure. The local group forms part of a larger structure called the Virgo supercluster. A supercluster is a collection of galaxy clusters and galaxy groups held together by gravity. The Virgo supercluster contains at least 100 galaxy groups and clusters, including our own local group. It measures about 110 million light-years across. At the heart of the Virgo supercluster lies the Virgo cluster, a massive collection of over 1,000 galaxies. This cluster dominates the gravitational landscape of our region of space. Its gravity pulls on the local group, drawing us slowly inward at hundreds of kilometers per second. This motion adds to the Hubble flow, the general expansion of the universe, creating a complex pattern of movement. The Virgo cluster contains giant elliptical galaxies, spiral galaxies like the Milky Way, and numerous dwarf galaxies. The largest galaxy in the cluster, Messier 87, is a supergiant elliptical galaxy containing several trillion stars. At its center lies a supermassive black hole with a mass of about 6 billion solar masses. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow by observing this object. The image showed a bright ring of light surrounding a dark central region, confirming predictions of general relativity. In 2014, astronomers redefined our cosmic address by discovering that the Virgo supercluster is merely a small section of an even larger supercluster called Laniakea. The name derives from Hawaiian words meaning immense heaven. Laniakea contains roughly 100,000 galaxies and extends about 520 million light-years across. To give you perspective, if the Milky Way were the size of a quarter, Laniakea would be roughly the size of the United States. Laniakea is defined not only by the galaxies it holds, but by how those galaxies are moving. All the galaxies in Laniakea are flowing toward a region called the Great Attractor, a gravitational anomaly positioned about 250 million light-years away in the direction of the Centaurus constellation. The Great Attractor itself is hidden behind the disk of the Milky Way, obscured by gas and dust. We cannot observe it directly in visible light, but we can detect its presence through its gravitational influence on surrounding galaxies. The Great Attractor is not a single object, but rather a massive concentration of matter, possibly containing tens of thousands of galaxies. Its gravity pulls on all the galaxies in Laniakea, including our own. We are falling toward it at about 600 kilometers per second. However, the expansion of the universe means we will never actually reach it. Space itself is expanding faster than we are moving, like running on a treadmill that speeds up faster than you can run. By mapping the velocities of thousands of galaxies, astronomers traced the flow patterns across Laniakea. They found that galaxies move along invisible channels, following the gravitational gradients created by the distribution of matter. These flow patterns define the boundaries of Laniakea, separating it from neighbouring superclusters with their own attractors and flow patterns. Now, you might assume that Laniakea, with its 520 million light-year diameter and its 100,000 galaxies, would rank among the largest structures in the universe, but it does not even come close. This leads us to the cosmic web. The universe is not spread evenly. Galaxies are not scattered randomly through space like stars on a flag. Instead, they arrange themselves into an intricate pattern, a vast cosmic web of filaments and voids that spans the entire observable universe. Imagine a three-dimensional spider web, but instead of silk threads, the filaments are made of galaxies. The threads stretch across hundreds of millions of light years, connecting massive clusters at the intersections. Between the threads lie enormous voids, regions of space nearly empty of galaxies, some measuring hundreds of millions of light years across. The pattern resembles foam in some ways. Think of soap bubbles clustered together. The walls of the bubbles represent the filaments and sheets where galaxies concentrate. The interiors of the bubbles represent the voids. The intersections where multiple bubbles meet represent galaxy clusters. This foam structure extends throughout all of space, as far as we can observe. This foam analogy is not perfect, but it captures the essential structure. The walls between voids are thin compared to the size of the voids themselves. Galaxies cluster in these walls, forming two-dimensional sheets and one-dimensional filaments. The densest concentrations occur where multiple walls meet, creating three-dimensional knots we call galaxy clusters. This cosmic web formed over billions of years through the action of gravity. In the early universe, tiny variations in density grew over time. Regions slightly denser than average pulled in more matter, becoming denser still. Regions slightly less dense than average lost matter to their neighbours, becoming emptier over time. The result is what we observe today, a universe organised on the largest scales into a web-like structure. The filaments mark where matter has been drawn together by gravity. The voids mark where matter has been pulled away. And it is within this cosmic web that we find the largest known object in the universe. In 2013, a team of astronomers announced the discovery of an enormous structure. They called it the Hercules-Corona Borealis Great Wall. But we are going to use a different name, one proposed by some astronomers, Quipu. The name comes from the ancient Incan recording system of knotted strings, which seems fitting for a structure that looks like a network of connected threads. The Incan Quipu was a sophisticated device for recording information. Knots, tied at different positions along strings, represented numbers and categories. The colour of the string, the direction of the knot, the spacing between knots, all carried meaning. Complex quipus could encode detailed records of tribute payments, census data, calendars, and possibly even narratives and songs. The strings hung from a main cord, branching and connecting in patterns that conveyed layers of information. Archaeologists have recovered hundreds of quipus, but deciphering them remains challenging. The Inca had no written language, relying instead on these knotted cords to record and transmit information across their empire. Some scholars believe quipus may have been a form of three-dimensional writing, encoding language itself in the patterns of knots and strings. The cosmic structure we call Quipu resembles this system in a poetic way. Galaxy clusters hang like knots along cosmic strings, connected in a vast network that spans unimaginable distances. The pattern, like the Incan Quipu, contains information. It tells us about the distribution of matter in the early universe, about how structure grows under gravity, about the fundamental properties of space and time. Quipu is a collection of galaxy clusters arranged along a massive filament in the cosmic web. It stretches across approximately 1.4 billion light-years of space. To put that in perspective, Quipu is about 10% of the diameter of the entire observable universe. If the observable universe were the size of Earth, Quipu would be about the size of the Atlantic Ocean. Let us pause here and consider what 1.4 billion light-years means. Light, which travels faster than anything in the universe, takes 1.4 billion years to cross Quipu from end to end. Our entire solar system is only about 4.5 billion years old. It would take light nearly 1/3 the age of our solar system to traverse this single structure. When we observe one end of Quipu, we see it as it was 1.4 billion years ago. When we observe the other end, we see it at a different epoch. The structure is so large that light from different parts has been travelling to us for different amounts of time. We are not seeing a snapshot of Quipu as it is now. We are seeing a composite image spanning hundreds of millions of years. Quipu contains 18 galaxy clusters that we know of, possibly more that we have not yet detected. Each of these clusters holds hundreds or thousands of galaxies. Each galaxy contains billions of stars. Each star might host planets. The total number of stars within Quipu likely exceeds the number of grains of sand on all the beaches of Earth. If you could somehow gather all the sand from every beach on Earth and count the grains, you might reach perhaps 7 quintillion grains. That is 7 followed by 18 zeros. Quipu contains more stars than that. The number becomes meaningless, a symbol rather than a quantity you can comprehend. And yet, each of those stars is a sun, a massive sphere of fusing hydrogen, potentially accompanied by worlds. So how did astronomers find something this large? The answer involves gamma-ray bursts, some of the most violent events in the universe. When certain massive stars reach the end of their lives, they collapse and explode in a specific type of supernova that produces a gamma-ray burst. These bursts are so bright they can be detected from billions of light-years away. For a brief moment, a gamma-ray burst can outshine the entire rest of the universe in gamma rays. The burst releases as much energy in a few seconds as our sun will produce over its entire 10 billion year lifetime. Gamma-ray bursts were first detected in the 1960s by satellites designed to monitor for nuclear weapons tests. The satellites saw brief flashes of gamma rays coming from space, not from Earth. The discovery remained classified for several years before being announced to the scientific community in 1973. Initially, the origin of these bursts was a mystery. It took decades of observations to understand gamma-ray bursts. They occur at random locations across the sky, multiple times per day somewhere in the universe. By measuring their distances, astronomers determined they originate from distant galaxies, billions of light-years away. This meant they must be extraordinarily energetic to be visible across such distances. Gamma-ray bursts come in two varieties. Short bursts last less than 2 seconds. They occur when two neutron stars spiral together and merge, or when a neutron star merges with a black hole. As the objects approach each other, they orbit faster and faster, emitting gravitational waves that carry away energy. Eventually, they touch, merge in a catastrophic collision, and release tremendous energy in all forms, including a brief pulse of gamma rays. Long bursts last more than 2 seconds, sometimes lasting for minutes. They occur when extremely massive stars, those with at least 20 or 30 times the mass of our Sun, exhaust their nuclear fuel and collapse. The core collapses into a black hole or neutron star, while the outer layers explode outward. If the star is rotating rapidly, the collapse can channel energy into narrow jets shooting out along the rotation axis. If Earth happens to lie in the path of one of these jets, we detect it as a gamma-ray burst. These jets are among the most extreme phenomena in the universe. They move at nearly the speed of light, carrying enormous energy. Material in the jets collides with surrounding gas, creating shocks that emit gamma rays, X-rays, and light across the electromagnetic spectrum. The afterglow can remain visible for days or weeks after the initial burst, allowing detailed study. By mapping the locations of gamma-ray bursts, astronomers noticed something unusual. In a particular region of the sky, in the direction of the constellations Hercules and Corona Borealis, there seemed to be more gamma-ray bursts than expected. This suggested there might be more galaxies in that direction, and more galaxies usually means a large-scale structure. Long gamma-ray bursts are associated with star formation. They occur when very massive stars exhaust their nuclear fuel and collapse. Because massive stars have short lifespans, only a few million years compared to 10 billion for stars like our Sun, gamma-ray bursts indicate regions where stars are forming actively. Young galaxies with vigorous star formation produce more massive stars and therefore more gamma-ray bursts. The discovery was not immediate. It required years of patient observation. Satellites like Swift and Fermi detected gamma-ray bursts and recorded their positions on the sky with increasing precision. Ground-based telescopes followed up, identifying the host galaxies and measuring their distances through spectroscopy. Spectroscopy involves splitting the light from a galaxy into its component wavelengths, revealing dark lines where specific elements absorb light. These lines are shifted toward redder wavelengths by the expansion of the universe, and the amount of shift tells us the galaxy's distance. Gradually, a pattern emerged. Many of the gamma-ray bursts in this region of sky came from galaxies at similar distances, between about 400 million and 800 million light-years away. Statistical analysis showed this clustering was unlikely to occur by chance. The probability of such a concentration arising randomly was very low, less than 1 in 10,000. Follow-up observations with optical and infrared telescopes confirmed it. There was indeed a massive concentration of galaxy clusters in that region. Large-scale surveys mapped the distribution of galaxies across the sky. When astronomers plotted the three-dimensional positions of galaxies in this direction, accounting for their distances, they revealed the structure. As more data came in, the full extent became clear. The structure was enormous, stretching across more than 1 billion light-years. Now, you might wonder, what holds something like Quipu together? The answer is gravity and dark matter. Galaxy clusters are the largest gravitationally bound structures in the universe. Each cluster contains hundreds or thousands of galaxies held together by gravity. But the visible galaxies only account for a small fraction of the total mass. Most of the mass in a galaxy cluster is dark matter, an invisible substance that does not emit light but exerts gravitational force. Dark matter outweighs visible matter by a ratio of about 6:1 in galaxy clusters. The dark matter forms a massive halo around each cluster, extending far beyond the visible galaxies. It is this dark matter that holds the cluster together against the expansion of space. We detect dark matter through its gravitational effects. When we measure how fast galaxies move within a cluster, we find they are moving too quickly. Typical galaxy speeds within clusters reach hundreds or thousands of kilometers per second. The visible matter in the cluster does not have enough gravity to hold them in place. The galaxies should fly apart and escape the cluster, but they do not. Something invisible provides additional gravity, keeping the galaxies bound. That something is dark matter. Another way we detect dark matter is through hot gas between galaxies. This gas, heated to millions of degrees, emits X-rays. By measuring the temperature and density of this gas, we can calculate how much gravity is needed to keep it from escaping. The answer always exceeds what visible matter can provide. Dark matter makes up the difference. Gravitational lensing provides yet more evidence. According to Einstein's general relativity, mass bends space-time, causing light to follow curved paths. Massive objects like galaxy clusters act as gravitational lenses, bending the light from more distant galaxies behind them. This creates distorted images, arcs, and sometimes multiple images of the same background galaxy. By carefully measuring these distortions, astronomers can map the distribution of mass in the cluster, including the dark matter. What they find is that most of the mass is indeed invisible, distributed in a large, diffuse halo that extends well beyond the visible galaxies. The dark matter distribution follows the distribution of galaxies, but is much more extended and massive. Between the clusters, along the filaments of the cosmic web, there is also dark matter. The filaments are like bridges of dark matter connecting the clusters. Galaxies fall along these bridges, drawn by gravity toward the densest regions at the intersections. Quipu is essentially a particularly massive and extended filament in the cosmic web. The clusters we observe mark the densest concentrations along that filament, but between the clusters there is still matter, both dark and visible, connecting them into a coherent structure. This raises an important question. Is Quipu a single object, or just a chance alignment of separate clusters? The answer depends on how you define object. If you require that an object be gravitationally bound, meaning all its parts are held together by their mutual gravity, then Quipu might not qualify as a single object. The clusters are so far apart that they may not be gravitationally bound to each other. The expansion of space might eventually pull them apart. But if you define object more loosely as a coherent structure that formed together and shares a common history, then Quipu does qualify. The clusters all formed from the same large-scale density fluctuation in the early universe. They are connected by filaments of dark matter. They move together through space as part of the same large-scale flow. They share a common origin and a common fate. Most astronomers lean toward the second interpretation. Quipu is a real structure, not a random alignment. It formed through a coherent physical process and represents a genuine feature of the cosmic web. To understand how Quipu formed, we need to go back to the early universe. About 380,000 years after the Big Bang, the universe became transparent for the first time. Before this, the universe was so hot and dense that light could not travel freely. Photons were constantly absorbed and re-emitted by electrons, creating a fog that filled all of space. Imagine trying to see through a thick cloud. Light scatters off water droplets in all directions, preventing you from seeing distant objects clearly. The early universe was similar, but instead of water droplets, free electrons scattered the light. Everywhere you looked, you would see glowing fog, the light of the Big Bang itself scattered and rescattered countless times. The entire universe was opaque, a featureless glow in all directions. But as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. This process, called recombination, happened when the universe cooled to about 3,000 degrees, cool enough for atoms to remain stable. With no free electrons to scatter them, photons could suddenly travel unimpeded across the universe. This moment released the light we now observe as the cosmic microwave background. The cosmic microwave background is radiation from the early universe, stretched and cooled by expansion into microwaves. When we map this radiation today, we see tiny temperature variations, patterns that reveal the distribution of matter in the early universe. These patterns show that matter was not distributed perfectly evenly. There were tiny fluctuations, regions slightly denser than average and regions slightly less dense. These fluctuations were incredibly small, differing from the average density by only about 1 part in 100,000. Imagine a perfectly smooth surface with bumps and dips only 1/10,000th the size of the surface itself. That is how smooth the early universe was. You could not see these variations with the naked eye. You would need precise instruments to detect them. And yet, those tiny imperfections were enough. These fluctuations originated even earlier, during a period called inflation. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light. This inflation smoothed the universe to near perfect uniformity, while simultaneously amplifying quantum fluctuations to cosmic scales. The pattern of hot and cold spots in the cosmic microwave background is a map of these primordial quantum fluctuations, blown up to the size of the observable universe. But gravity amplified these tiny differences over billions of years. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their neighbours, becoming emptier. Over time, the small fluctuations grew into the cosmic web we see today. Quipu began as one of these fluctuations. Roughly 13 billion years ago, there was a region of space slightly denser than its surroundings. This region was enormous, spanning what would eventually become more than 1 billion light years. It was perhaps 1% denser than the surrounding universe, a tiny difference, but that was enough. As the universe expanded, matter fell into this region, drawn by gravity. The matter did not fall evenly. It followed the patterns set by smaller fluctuations within the larger one. This created a web-like structure even within the larger density enhancement. Some regions became denser, faster, forming the first galaxy clusters. Other regions became the filaments connecting them. Over billions of years, the matter continued to collapse and organize. The densest regions became galaxy clusters. Thousands of galaxies fell together, their mutual gravity holding them in place. The filaments connecting them became visible as chains of galaxies, smaller groups, and isolated giants. The voids between them grew larger and emptier as matter drained away toward the clusters. By about 7 billion years ago, Quipu had taken on roughly its current form. The galaxy clusters had formed and were actively pulling in more matter. The structure continued to evolve, but the basic pattern was established. Today, 13.8 billion years after the Big Bang, Quipu remains a prominent feature of the cosmic web. The clusters continue to accrete matter. The filaments continue to channel galaxies toward the clusters. The structure is still evolving, but at a much slower pace than in the past. One of the most remarkable things about Quipu is how statistically improbable it is. Remember, the fluctuations in the early universe were tiny, only about 1 part in 100,000. Most fluctuations were small, affecting regions only millions or tens of millions of light years across. Large fluctuations affecting regions hundreds of millions or billions of light years across were extremely rare. The statistics of cosmic structure formation follow what mathematicians call a Gaussian distribution. Small fluctuations are common. Large fluctuations are rare. Extremely large fluctuations are extremely rare. Quipu represents an unusually large fluctuation, one that falls in the tail of the distribution. The probability of finding a fluctuation large enough and strong enough to produce something like Quipu is very low. Some calculations suggest structures like Quipu should occur only about once in several billion cubic light years of space. Our observable universe contains about 300 billion cubic light-years. So statistically, we might expect to find a few dozen structures similar to Quipu in the entire observable universe. Finding one is not shocking, but finding many would suggest something is wrong with our understanding. This has led some astronomers to question whether our understanding of cosmology is complete. If structures like Quipu are too rare according to our models, maybe our models need adjustment. Maybe the early universe had slightly larger fluctuations than we thought. Maybe inflation worked slightly differently than our current theories predict. Maybe dark energy or dark matter behaves slightly differently than we assume. Or maybe we simply got lucky. The universe is vast, and rare things do happen occasionally. Just because something is improbable does not mean it is impossible. Flip a coin 1,000 times, and you will occasionally get runs of 10 heads in a row. Such runs are unlikely, but they happen. One Quipu in our observable universe might be perfectly consistent with our models, just an unlikely but allowed outcome. Current data suggests the second interpretation is more likely. Quipu is unusual, but not so unusual that it breaks our models. It is rare, but not impossible. It lies near the edge of what we expect, but not beyond it. We do not need to invoke new physics to explain it, though the possibility remains open. Quipu is not the only large-scale structure we have discovered. There are others, each remarkable in its own way. The Sloan Great Wall, discovered in 2003, stretches about 1.37 billion light-years across. It is a massive filament containing thousands of galaxies, located about 1 billion light-years from Earth. For several years, it held the record as the largest known structure. The discovery came from the Sloan Digital Sky Survey, a project that mapped millions of galaxies across a large fraction of the sky. By plotting galaxy positions in 3 dimensions, astronomers revealed vast wall-like structures spanning enormous distances. The CFA-2 Great Wall, discovered earlier in 1989, stretches about 500 million light-years and was the first giant structure of its kind to be found. Its discovery shocked astronomers, who had not expected to find structures so large. At the time, cosmological models suggested structures this big should not exist. Their discovery prompted revisions to our understanding of how cosmic structure forms. The giant GRB ring, discovered in 2015, is a ring-shaped arrangement of gamma-ray bursts with a diameter of about 5.6 billion light-years. If it is a real structure and not a statistical fluctuation, it would be enormous, far larger than Quipu. But its existence remains debated. Some astronomers think it might be a chance alignment rather than a physically connected structure. The evidence for the giant GRB ring comes from the spatial distribution of gamma-ray bursts, which appear to form a rough circle on the sky. But verifying whether this represents a real 3-dimensional ring or merely a chance projection requires careful statistical analysis. The debate continues, with some studies supporting its reality and others suggesting it may be a statistical artifact. The Claus-Campusano Large Quasar Group, discovered in 1991, is a collection of 73 quasars, spanning about 4 billion light-years. Quasars are extremely bright galactic cores powered by supermassive black holes. They are among the most luminous objects in the universe, visible across billions of light-years. Quasars occur when supermassive black holes actively consume matter. Gas spirals into the black hole, forming an accretion disk that heats to millions of degrees. This disk can outshine the entire rest of the galaxy, making quasars visible across enormous distances. Finding many quasars in a concentrated region suggests an underlying large-scale structure, a region with an unusually high concentration of galaxies and gas. The huge large quasar group, discovered in 2013 around the same time as Quipu, spans about 4 billion light-years and contains 73 quasars. Like other quasar groups, it hints at enormous concentrations of matter in the early universe. The light from these quasars has been travelling for billions of years, showing us the universe when it was much younger. Each of these structures challenges our understanding in different ways. Each pushes the limits of how large structures can grow in the time available since the Big Bang. Each raises questions about the formation and evolution of the cosmic web. But among all of them, Quipu remains the largest single coherent structure we have found. Its 1.4 billion light-year span makes it the current record holder. Whether it will remain the largest depends on future discoveries. As our telescopes improve and our surveys cover more of the sky, we might find something even larger. Next-generation telescopes like the Vera Rubin Observatory will survey the entire southern sky repeatedly, mapping billions of galaxies. The Euclid Space Telescope will map the three-dimensional distribution of galaxies across a third of the sky. These surveys will reveal the cosmic web in unprecedented detail. Or we might determine that Quipu represents a fundamental limit, the maximum size a structure can reach given the age and expansion rate of the universe. The balance between gravity, which builds structure, and dark energy, which drives expansion, sets limits on how large structures can grow. Quipu may be close to that limit. Only time and more observations will tell. To truly appreciate Quipu, we need to understand the cosmic web in more detail. The cosmic web is not a static structure. It is dynamic, constantly evolving as matter flows along the filaments and accumulates in the clusters. Think of the filaments as highways for galaxies. Galaxies move along these paths, drawn by gravity toward the densest regions. As they travel, they interact with other galaxies, sometimes merging, sometimes passing by. The journey can take billions of years. A galaxy might fall along a filament for hundreds of millions of years before reaching a cluster. A galaxy falling along a filament toward a cluster experiences gradually increasing gravitational force. At first, when the galaxy is far from the cluster, the attraction is gentle. The galaxy maintains its shape and continues forming stars normally. Its spiral structure remains intact. Its disk of gas continues to rotate. New stars continue to ignite in its spiral arms. But as the galaxy approaches the cluster, the gravitational field strengthens. Tidal forces begin to pull on the galaxy, stretching it slightly in the direction of the cluster. Gas within the galaxy feels these forces too. If the galaxy passes close to other galaxies, gravitational interactions can trigger bursts of star formation, compress gas clouds, or strip away the galaxy's outer regions. Once a galaxy enters a cluster, its environment changes dramatically. The space between galaxies in a cluster is filled with hot gas. As the galaxy moves through this gas at hundreds of kilometers per second, it experiences ram pressure, like driving into a headwind. This pressure can strip gas away from the galaxy, removing the raw material for future star formation. Over time, the galaxy becomes quiescent, its star formation ceasing as its gas supply dwindles. The voids between filaments are not completely empty. They contain isolated galaxies, small groups, and diffuse gas. But they are underdense compared to the filaments. Matter continues to flow out of the voids and into the filaments, making the voids emptier over time and the filaments denser. Now let us look more closely at what galaxy clusters actually are. A galaxy cluster is a collection of galaxies bound together by gravity. Typical clusters contain hundreds to thousands of galaxies. The galaxies are not stationary. They orbit within the cluster, moving at speeds of hundreds or thousands of kilometers per second. These velocities are so high that if the galaxies were not gravitationally bound, they would escape the cluster in less than 1 billion years. Despite these high speeds, the galaxies remain bound because the total mass of the cluster is enormous. Most of that mass is dark matter. If you could see dark matter, a galaxy cluster would appear as a giant diffuse halo with the visible galaxies embedded within it like raisins in bread. The dark matter extends well beyond the visible galaxies, creating a gravitational well that holds everything together. The ratio of dark matter to visible matter in clusters is about 6:1. For every kilogram of ordinary matter in stars, gas, and planets, there are 6 kilograms of dark matter. This ratio appears consistent across different clusters and different scales, one of the key pieces of evidence that dark matter is real and pervasive. Between the galaxies, there is also gas. This gas is extremely hot, millions of degrees Celsius, heated by the gravitational collapse of the cluster and by energy released from galaxies and black holes. The hot gas emits X-rays, which we can detect with space-based X-ray telescopes like Chandra and XMM Newton. The gas between galaxies in a cluster can be hotter than the surfaces of stars. Typical temperatures reach tens of millions of degrees, far hotter than anything we can create on Earth, even in nuclear fusion reactors. This extreme heat comes from the potential energy of the gas falling into the cluster's gravitational well. As the gas falls inward, it gains speed, and collisions between particles convert this kinetic energy into heat. The total mass of gas in a cluster can exceed the total mass of stars. There is more matter between the galaxies than in the galaxies themselves. This hot gas glows brilliantly in X-rays, creating extended halos around clusters visible to X-ray telescopes. By mapping the X-ray emission, astronomers can study the distribution of the gas, measure its temperature and density, and infer the distribution of dark matter. The total mass of a typical large galaxy cluster is about 1 quadrillion solar masses. That is 1 followed by 15 zeros times the mass of our Sun. To put this in perspective, the Milky Way galaxy contains about 1 trillion solar masses. A large galaxy cluster contains about 1,000 times as much mass as the Milky Way. Of that mass, about 85% is dark matter, 10% is hot gas, and only 5% is in the form of stars and planets within galaxies. The visible part of the universe, the part we can see with our telescopes, is just the tip of the iceberg. Most of the universe is invisible. Dark matter and dark energy together make up about 95% of the total energy density of the universe. Ordinary matter, the stuff we are made of, the stuff we can see and touch, accounts for only about 5%. We are made of the minority component of the universe. Within Quipu, there are 18 known galaxy clusters, each with a mass around 1 quadrillion solar masses or more. Multiply that by 18, and you get a total mass of about 18 quadrillion solar masses, possibly more if there are additional undetected clusters. That is an almost unimaginable amount of matter, organized into a single coherent structure. These clusters are not isolated. They are connected by filaments of dark matter and gas. Along these filaments, there are additional galaxies, groups, and diffuse matter. The total mass of Quipu, including all the filaments and the space between clusters, likely exceeds the 18 quadrillion figure significantly. Estimating the total mass is difficult because much of it is in the form of dark matter and diffuse gas that is hard to detect. Dark matter does not emit light, so we cannot see it directly. Diffuse gas between clusters is much cooler than the hot gas within clusters, making it harder to detect. But conservative estimates place Quipu's total mass at tens of quadrillions of solar masses. That is more mass than in millions of Milky Way-sized galaxies, all organized into a single structure spanning more than 1 billion light-years. When we observe Quipu, we are not seeing it as it is now, we are seeing it as it was in the past. Light takes time to travel, so when we look at distant objects, we see them as they were when the light left them, not as they are today. This effect, called look-back time, means astronomy is a form of time travel. The farther we look, the further back in time we see. The nearest parts of Quipu are about 425 million light-years away. The farthest parts are about 800 million light-years away. This means we are seeing different parts of Quipu at different times in its history, separated by about 375 million years. This gives us a window into how the structure has evolved over time. By comparing the properties of the nearer clusters to the more distant ones, we can study how clusters change as they age. What we observe is generally consistent with our models. Older clusters, the ones we see more recently in cosmic time, tend to be more massive, having had more time to accrete matter. They have more regular shapes, having had more time for gravitational interactions to smooth out irregularities. Younger clusters, the ones we see at earlier times, are more chaotic, still in the process of merging with smaller groups and assembling their final form. They often show signs of recent collisions, with distorted X-ray emission patterns and disturbed galaxy distributions. The galaxies have not yet settled into smooth orbits. The gas has not yet reached equilibrium. Over time, these irregularities settle down as the cluster relaxes into a more stable configuration. The structure as a whole appears stable. The clusters are not flying apart, nor are they collapsing together. They maintain roughly constant separations, held in balance by the expansion of space and the gravitational attraction between them. This balance is delicate but persistent. Quipu has maintained its structure for hundreds of millions of years and will continue to do so for billions more. Over the next billions of years, Quipu will continue to evolve slowly. The clusters will grow slightly more massive as they continue to accrete matter from their surroundings. The filaments will continue to channel matter toward the clusters. Individual galaxies will merge, grow, and evolve, but the overall structure will persist, a permanent feature of the cosmic web until the very distant future. In the far future, trillions of years from now, the accelerating expansion driven by dark energy will tear even these great structures apart. Clusters will become isolated islands in an ever-expanding ocean of space. The galaxies within each cluster will remain bound to each other, but the clusters will lose contact with one another. The cosmic web will dissolve, leaving behind isolated clusters drifting through an increasingly empty universe. But that end lies so far in the future that it seems almost irrelevant to the present. Let us consider the method used to discover Quipu in more detail. Gamma-ray bursts are brief, intense flashes of gamma rays, the highest energy form of light. They last from a few milliseconds to several minutes. During that time, they can outshine the entire rest of the universe in gamma rays. These are the most luminous electromagnetic events known to occur in the universe. There are two main types of gamma-ray bursts. Short bursts, lasting less than 2 seconds, are thought to come from the merger of two neutron stars or a neutron star and a black hole. These mergers are among the most violent events imaginable. Two city-sized objects, each containing more mass than the Sun, collide at a significant fraction of the speed of light. The collision releases as much energy in a few seconds as the Sun will emit over billions of years. Long bursts, lasting more than 2 seconds, come from the collapse of massive stars. When a star more than 25 or 30 times the mass of the Sun exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses in less than a second, forming a black hole or neutron star. The outer layers fall inward, then bounce off the incompressible core and explode outward in a supernova. If the star is rotating rapidly, the collapse can form jets of material shooting out along the rotation axis at nearly the speed of light. These jets drill through the star's outer layers and escape into space, carrying enormous energy. If Earth happens to lie along the direction of one of these jets, we see a gamma ray burst. If we are off-axis, we see only the supernova. Bright, but not as extreme. Long gamma ray bursts are associated with star formation. They occur when very massive stars exhaust their nuclear fuel and collapse. Because massive stars have short lifespans, only a few million years compared to 10 billion for stars like our Sun, gamma ray bursts indicate regions where stars are forming actively. Massive stars are rare but important. Only about 1 in every few hundred stars is massive enough to produce a gamma ray burst. But these stars dominate their environments. They emit tremendous amounts of ultraviolet radiation, ionizing surrounding gas and creating glowing nebulae. They produce strong stellar winds that blow away gas, creating bubbles in the interstellar medium. When they explode, they inject heavy elements into space and trigger new waves of star formation in compressed surrounding gas. Galaxy clusters contain hot gas that emits X-rays. By measuring the temperature and distribution of this gas, we can calculate how much gravity is needed to hold it in place and keep it from escaping. The answer is always much more than the visible matter can provide. The gas is so hot it should evaporate and disperse unless something is holding it gravitationally. That something is dark matter, providing the extra gravity needed to confine the gas. Gravitational lensing provides more evidence. Massive objects bend the path of light passing near them, a prediction of Einstein's general relativity confirmed by observations during a solar eclipse in 1919. Galaxy clusters act as giant lenses, distorting the images of background galaxies. By measuring this distortion, we can map the distribution of mass in the cluster, including the dark matter. Gravitational lensing sometimes creates dramatic visual effects. Background galaxies appear as arcs or multiple images, smeared around the cluster like reflections in a funhouse mirror. In some cases, the lensing is so strong it creates Einstein rings, perfect circles of light surrounding the lensing mass. The most famous example is the cosmic horseshoe, where a distant galaxy is lensed into a nearly complete ring around a foreground galaxy cluster. These phenomena allow us to weigh galaxy clusters with great precision. We can map how mass is distributed, separating the contribution of visible matter from dark matter. What we consistently find is that most of the mass is invisible, distributed in large halos, extending well beyond the visible galaxies. The dark matter distribution follows the distribution of galaxies, but is much more extended and massive. All of these observations, from galaxy rotation curves to cluster dynamics to gravitational lensing, point to the same conclusion. There is matter we cannot see, present in large amounts, holding galaxies and clusters together. Without dark matter, structures like Quipu could not exist. The visible matter alone does not have enough gravity to hold such a large structure together against the expansion of space. Dark matter provides the scaffolding. It forms the filaments and halos that guide the visible matter. Galaxies form within dark matter halos, like condensation forming in clouds. Dark matter determines where galaxies appear and how they move. The cosmic web is fundamentally a dark matter web, with visible galaxies marking the densest regions. We do not know what dark matter is made of. The leading candidates are hypothetical particles that interact only through gravity and possibly the weak nuclear force. These particles would have been produced in the early universe and would still be around today, filling space with invisible matter passing through ordinary matter without interacting. The first stars, called population 3 stars, were likely very massive, containing only hydrogen and helium, no heavy elements. They burned hot and bright, living fast and dying young in spectacular supernovae after only a few million years. These supernovae enriched the surrounding gas with the first heavy elements, seeding future generations of stars with carbon, oxygen, iron, and other elements necessary for planets and life. Around 1 billion years after the Big Bang, galaxies began to cluster. Small groups formed first, then larger clusters as groups merged. The cosmic web began to take shape, with matter flowing along filaments into the growing clusters. This hierarchical assembly continues to the present day, with small structures merging into larger ones, in a process that will continue for billions of years to come. By about 7 billion years after the Big Bang, roughly the time Quipu was forming, the cosmic web had developed its basic structure. Filaments connected clusters, voids had formed between them, and the largest structures like Quipu were in place. The universe looked in broad outline, similar to how it looks today. The details continued to evolve, but the overall pattern was established. From 7 billion years ago to today, the cosmic web has continued to evolve. Clusters have grown more massive by accreting smaller groups and isolated galaxies. Voids have become emptier as matter drains toward filaments and clusters. Galaxies have merged, grown, and evolved, transforming from young star-forming spirals to old quiescent ellipticals in many cases. But the overall pattern of the cosmic web has remained relatively stable. The accelerating expansion driven by dark energy has prevented the web from collapsing or forming much larger structures. About 5 billion years ago, the expansion began to accelerate. Before that, gravity had been slowing the expansion, though not enough to reverse it. But dark energy's repulsive effect has gradually overwhelmed gravity on large scales, causing the expansion to speed up. This acceleration limits how large structures can grow. If gravity had continued to dominate, matter from ever larger distances could have fallen together, creating structures even bigger than Quipu. But dark energy prevents this. The accelerating expansion carries distant matter away faster than gravity can pull it together. Quipu may represent one of the largest structures that can form in a universe with dark energy. Quipu formed during a critical period in cosmic history. Earlier, the universe was too young for such large structures to have assembled. The matter was still too spread out. Gravity had not yet had enough time to pull it together. Later, the accelerating expansion would prevent structures from growing much larger. Matter at great distances moves away too quickly to ever fall together. Quipu represents a structure that formed at the right time, in the right place, under the right conditions. Its existence is a testament to the power of gravity to organize matter, even over distances of more than 1 billion light-years, even against the expansion of space. The fact that we can observe and study Quipu is remarkable. We are looking back across most of cosmic history, seeing a structure that formed when the universe was roughly half its current age. We are piecing together its history from incomplete data, using clever techniques and theoretical models. We cannot run experiments on Quipu. We cannot manipulate it or study it in a laboratory. We can only observe it from afar, from a single vantage point in space and time. And yet, despite these limitations, we have succeeded in mapping this enormous object and understanding how it fits into the larger cosmic web. This achievement speaks to the power of the scientific method and the ingenuity of astronomers. By combining observations across different wavelengths, from gamma rays to radio waves, by using statistics and computer simulations, by building on centuries of accumulated knowledge, we have revealed the largest structures in the universe. We have mapped the cosmic web across billions of light years. We have traced the history of the universe from the Big Bang to the present. These are among the greatest intellectual accomplishments in human history. Future telescopes will allow even more detailed studies. The Athena X-ray Observatory, planned for launch in the 2030s, will have unprecedented sensitivity and spectral resolution. It will measure the velocities of gas within clusters, track turbulence, map temperature variations in detail. The Lynx X-ray Observatory, still in the planning stages, would push sensitivity even further, potentially detecting individual supernova remnants within distant clusters. By mapping the temperature, density, composition, and velocity of the gas in each cluster within Quipu, we can reconstruct the history of energy injection and matter accretion. We can test our models of how supermassive black holes grow and how they affect their surroundings. We can watch the cosmic web evolve over time, seeing how structures grow and change across cosmic history. Another important aspect is the role of cosmic filaments in channeling matter. The filaments of the cosmic web are not empty tubes. They contain gas, galaxies, and dark matter, all moving together along the gravitational potential gradient toward the clusters at the filament ends. Matter flows along these filaments toward the clusters at their intersections. The flow is not smooth or uniform. Galaxies move in clumps and streams, following the gravitational field created by the dark matter distribution. Some galaxies fall directly toward clusters along the filament axis. Others orbit around the filament, spiraling slowly inward. Some galaxies fall directly into clusters, plunging through the cluster center at high speed. Others orbit around clusters for billions of years before eventually falling in, making multiple passages through the outskirts. Some never fall in at all, remaining in the filaments indefinitely. The journey can take billions of years, with galaxies traveling hundreds of millions of light years along filaments. As galaxies move along filaments, they encounter gas from the filament and gas from other galaxies. These interactions can trigger star formation, compressing gas clouds until they collapse and ignite nuclear fusion. Newly formed stars light up the galaxies, creating bursts of bright blue light from hot young stars. Or the interactions can strip gas away from galaxies, removing the raw material for future star formation and quenching star formation entirely. The fate of a galaxy depends on its mass, its environment, and its history. Small galaxies, those with masses less than 1/10 of the Milky Way, are more easily affected by their environment. They can lose their gas quickly when entering a cluster, or even when moving through gas-rich regions of filaments. The gas is stripped away by ram pressure or by tidal forces, leaving behind a red and dead galaxy no longer capable of forming stars. Large galaxies, those comparable to or larger than the Milky Way, are more resistant to environmental effects. They can retain their gas longer and continue forming stars even in dense environments. Their deeper gravitational wells hold onto gas more tightly. It takes more extreme conditions to quench their star formation, but even large galaxies eventually succumb if they remain in clusters long enough. The filaments themselves are interesting structures deserving more attention. They have typical widths of tens of millions of light years and lengths of hundreds of millions of light years. They are roughly cylindrical, though with irregular cross-sections. Some are thick and massive, containing many galaxies. Others are thin and tenuous, containing only a few. Filaments contain about half of all the matter in the universe. The other half is split between clusters, which contain about a quarter, and voids, which contain the remaining quarter. But because filaments cover such large volumes, their average density is much lower than in clusters. A filament might contain only 10 or 20 times the average density of the universe, while a cluster contains hundreds or thousands of times the average density. Observing filaments directly is challenging. They are much less dense than clusters, so they emit less light and are harder to detect. The gas in filaments is cooler than in clusters, making it less visible in X-rays. The galaxies in filaments are spread out, making them harder to identify as part of a coherent structure. But with deep surveys and careful analysis, astronomers have mapped hundreds of filaments, confirming their existence and properties. Within Quipu, the filaments connecting the clusters are particularly massive and prominent. They channel enormous amounts of matter, creating a continuous flow from the surrounding regions into the clusters. The filaments are the arteries of the cosmic web, carrying matter from the voids to the clusters where it accumulates. Mapping these filaments requires combining data from multiple wavelengths and techniques. Optical surveys reveal the galaxies, showing where visible matter is located. X-ray observations reveal the hot gas, though this is challenging in filaments where the gas is cooler and more diffuse. Gravitational lensing studies reveal the dark matter, mapping how mass distorts the light from background galaxies. Together, these observations give a complete picture of the structure. We can see where the visible matter is, where the dark matter is, how they are distributed, and how they are connected. We can trace the flow of matter through the cosmic web, watching as galaxies fall along filaments toward clusters, as gas is heated or cooled, as structures grow and evolve. Understanding the filaments is key to understanding Quipu as a whole. The filaments are not just passive connections between clusters. They actively shape the evolution of the structure, determining which clusters grow fastest and how matter is distributed across the system. They are the highways along which cosmic evolution proceeds. Heavy elements deserve more attention because they tell us about the history of star formation across cosmic time. The universe began with only hydrogen and helium, plus trace amounts of lithium. All the other elements, everything in the periodic table, from carbon to uranium, were created inside stars or in stellar explosions. Stars are element factories. In their cores, hydrogen fuses into helium, releasing energy that makes stars shine. More massive stars can fuse helium into carbon and oxygen. Even more massive stars continue the process, fusing carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each step releases less energy than the previous one. By the time a star reaches iron, fusion no longer produces energy. The star's core becomes inert. For the most massive stars, this leads to catastrophe. Without energy production to support the star against gravity, the core collapses in less than a second. The outer layers fall inward, then bounce off the incompressible core and explode outward in a supernova. The explosion creates elements heavier than iron through neutron capture, scattering these freshly synthesized elements into space. The heaviest elements, like gold and platinum, are created in even more exotic events. When two neutron stars merge, they briefly create conditions of extreme temperature and density. Rapid neutron capture can build up elements all the way to uranium and beyond. These rare events contribute a small but crucial fraction of the heavy elements in the universe. Over time, the gas in the universe becomes enriched with heavy elements. Each generation of stars adds more. The first stars, population 3, formed from pure hydrogen and helium. They lived and died, enriching the gas with the first heavy elements. The second generation, population 2, formed from slightly enriched gas containing perhaps 0.1% heavy elements. They added more heavy elements when they died. By the time our Sun formed, about 4.5 billion years ago, the gas in our region of the galaxy contained about 2% heavy elements. This enrichment was essential for planet formation. Rocky planets, like Earth, are made primarily of elements like iron, oxygen, silicon, and magnesium, all produced in previous generations of stars. The carbon, nitrogen, and oxygen in our bodies, the calcium in our bones, the iron in our blood, all were forged in stars that died billions of years ago. Today, the gas in galaxies and galaxy clusters contains a mix of hydrogen, helium, and heavy elements. The exact proportions depend on the history of star formation in that region. Regions that have experienced vigorous star formation over billions of years have higher heavy element abundances. Regions with less star formation retain compositions closer to the primordial mixture. By measuring the abundance of heavy elements, astronomers can infer how much star formation has occurred. This technique, called chemical archaeology or galactic archaeology, allows us to reconstruct the star formation history of galaxies and clusters. It connects the chemical composition we observe today to the history of stellar evolution stretching back billions of years. Within Quipu, the galaxy clusters contain hot gas enriched with heavy elements. X-ray spectroscopy can measure the abundances of elements like iron, oxygen, silicon, sulfur, and others. The enrichment levels vary from cluster to cluster and within individual clusters. Some clusters show high enrichment, with iron abundances 10 or 20% of the abundance in our Sun. Others show lower enrichment, only a few percent of solar. These variations reflect differences in star formation history. Clusters with high enrichment have hosted many generations of stars, particularly massive stars that produce large amounts of heavy elements. Clusters with lower enrichment formed more recently, or in regions with less vigorous star formation, or have been diluted by the infall of pristine gas from the surrounding cosmic web. The enrichment also varies spatially within individual clusters. The centers tend to be more enriched than the outskirts. This makes sense because cluster centers contain more galaxies concentrated in a smaller volume. More galaxies means more stars, more supernovae, more heavy elements released into the surrounding gas. But even the outskirts of clusters, hundreds of thousands or millions of light years from the center, show some enrichment. This indicates that heavy elements have been transported across large distances, perhaps by galactic winds driven by supernovae and stellar radiation, or by the powerful jets from supermassive black holes mixing the gas. Over billions of years, these processes have spread heavy elements throughout the cluster and even into the surrounding filaments. The heavy elements in Quipu were created over billions of years in countless stars. Some of those stars lived and died long ago when the universe was young, enriching the gas that formed later generations of stars and galaxies. Some are dying now, continuing the enrichment process. Some stars in Quipu's galaxies will continue forming heavy elements for trillions of years to come, though at a much slower rate as gas supplies dwindle. The presence of heavy elements connects Quipu to the entire history of stellar evolution in the universe. Every atom of oxygen in the hot intracluster gas, every atom of carbon in the stars, every atom of iron was forged in a star and scattered by its death. The cosmic web is not just a map of where matter is located, it is a record of where stars have lived and died, where galaxies have formed and evolved, where the universe has transformed itself from a simple mixture of hydrogen and helium into the rich, complex, chemically diverse environment we observe today. This chemical evolution is one of the great stories of cosmic history. The universe began simple and has become complex. It began with 2 elements and now contains more than 90 naturally occurring elements, plus traces of short-lived radioactive elements created in recent stellar explosions. It began with no structure and has developed structures on all scales, from planets to superclusters. It began lifeless and has produced, at least on Earth and possibly elsewhere, living organisms capable of contemplating their origins. Cosmic archaeology is the study of how the universe has changed over time. By observing objects at different distances, we observe them at different times in the past because light takes time to travel. This allows us to study cosmic history directly, watching how galaxies, stars, and structures have evolved. We can compare young galaxies in the distant universe, seen as they were billions of years ago, to old galaxies nearby, seen as they are in the relatively recent past. We can study how galaxies have grown through mergers, how their star formation rates have changed, how their morphologies have transformed. We can trace the assembly of the cosmic web, seeing how filaments and clusters have grown over cosmic time. For Quipu, we are seeing the structure as it was between 425 million and 800 million years ago, depending on which part we are observing. This is recent on cosmic timescales. The universe is 13.8 billion years old, so we are seeing Quipu when it was already quite mature, roughly 97% of the current age of the universe. But there are still differences between the nearer and more distant parts that allow us to study evolution. By comparing the properties of the nearer clusters, seen more recently in cosmic time, to the more distant ones, seen earlier, we can study how clusters change as they age over hundreds of millions of years. What we find is gradual evolution. The clusters have grown slightly more massive over this time span. The nearer clusters tend to have higher masses on average, having had more time to accrete matter from their surroundings. The galaxies within the clusters have evolved, with some continuing to form stars vigorously, while others have become quiescent, their star formation quenched by environmental processes. The overall structure has remained stable over this period. The positions of the clusters relative to each other have not changed dramatically. The filaments connecting them persist. Quipu has maintained its identity as a coherent structure. This matches our theoretical expectations. Once a structure like Quipu forms, it persists for billions of years. The expansion of space prevents it from collapsing into a single massive object. The mutual gravity of the clusters prevents them from flying apart completely. The result is a long-lived, relatively stable structure that evolves slowly over cosmic time. Looking further back in time, before Quipu formed, we would see a different picture. 7 or 8 billion years ago, the matter that would eventually become Quipu was spread over a larger region, less concentrated, still flowing inward along the developing filaments. Galaxy clusters were smaller, less massive, still actively assembling through mergers. The cosmic web was less pronounced, the contrast between filaments and voids less extreme. Going back even further, to the cosmic microwave background emitted when the universe was only 380,000 years old, we would see only the tiny density fluctuations that seeded Quipu. A region of space perhaps 1% denser than average, barely distinguishable from its surroundings. Nothing in the cosmic microwave background would obviously mark this region as special. And yet, this tiny overdensity was destined to grow over billions of years into the largest structure we know. This deep time perspective is one of the most profound insights of modern cosmology. We can trace the history of structures from the earliest moments after the Big Bang to the present day. We can watch them grow, evolve, and interact across billions of years of cosmic time. We can see how tiny quantum fluctuations in the first fraction of a second after the Big Bang evolved into galaxies, clusters, and the cosmic web. We are not just mapping the universe as it appears today. We are watching it unfold across cosmic time, seeing how it has changed and evolved, understanding the processes that have shaped it. This is time travel through observation, using the finite speed of light to look back across cosmic history. Cosmic variance is an important concept for understanding how much we can learn from observing a single structure like Quipu. The universe is large, much larger than the part we can observe from Earth. Our observable universe, the region from which light has had time to reach us since the Big Bang, is limited by the speed of light and the age of the universe. Light from regions more than about 46 billion light-years away has not had time to reach us. That 46 billion light-years, not 13.8 billion, is due to the expansion of the universe. As light travels toward us, space itself expands, increasing the distance to the object that emitted the light. The current size of the observable universe is about 93 billion light-years across. Beyond that distance, we cannot see. There might be more universe out there, possibly infinite in extent, but it remains forever beyond our observation. Light from those regions will never reach us, because the expansion of space is carrying them away faster than light can travel toward us. Within our observable volume, the distribution of matter is determined by the specific pattern of density fluctuations that occurred during inflation. These fluctuations are thought to be random, arising from quantum processes in the early universe. A different random realization would produce a different pattern of fluctuations, leading to a different arrangement of galaxies and clusters in the evolved universe. Observers in other parts of the universe, beyond our observable volume, would see different structures. They would see different galaxies, different clusters, different large-scale patterns. The overall statistics would be the same average density, the same types of structures, the same physical laws, but the specific details would differ. This randomness means we cannot learn everything about the universe from just our observable volume. We see only one realization of the cosmic web, one particular arrangement of matter that resulted from one particular pattern of primordial fluctuations. We do not know how typical or unusual our observable universe is compared to other regions we cannot see. This limitation is called cosmic variance. It affects our ability to measure certain properties of the universe, especially properties of rare objects like Quipu. It introduces an irreducible uncertainty into cosmological measurements that cannot be overcome by better observations or more precise instruments. Finding one structure like Quipu in our observable volume does not tell us precisely how common such structures are throughout the universe. We might have been lucky, observing a very rare fluctuation that occurs only once in a trillion cubic light-years. Or structures like Quipu might be common, occurring once in every few billion cubic light-years, and we happen to be in a typical region that contains one. To address this, astronomers run computer simulations of structure formation. They start with the known laws of physics, the measured properties of dark matter and dark energy, and the observed pattern of fluctuations in the cosmic microwave background. Then they simulate how structure forms over billions of years as the universe expands and gravity pulls matter together. Crucially, they run many simulations with different random initial conditions, each one representing a different possible realization of the early universe. They then average over many realizations, asking statistical questions. How often does a structure like Quipu appear? In what fraction of simulated universes do we find structures this large? What is the expected number of such structures in a volume the size of our observable universe? By asking how often structures like Quipu appear in the simulations, they can estimate how unusual it is. Current simulations suggest Quipu is rare, but not impossibly so. Structures this large, filaments containing 18 or more galaxy clusters and extending over more than 1 billion light-years, appear in perhaps 1 in 100 or 1 in 1,000 similar volumes. This means finding one in our observable universe is somewhat lucky, but not shocking. If we divided the observable universe into 1,000 equal volumes and checked each one, we might find 0, 1, 2, or possibly a few such structures. Finding one is perfectly consistent with this prediction. Finding 10 or 20 would be surprising and might suggest our models need revision. We do not need to revise our theories of cosmology to explain Quipu. Its existence is unlikely, but allowed within our current understanding. It represents a large statistical fluctuation, a rare but natural outcome of the same processes that created all cosmic structure. However, the uncertainty remains. Simulations are only as good as the physics they include and the assumptions they make. If our understanding of dark matter is incorrect, if dark matter particles interact in ways we have not accounted for, the simulations might produce incorrect predictions. If dark energy behaves differently than we assume, if its strength has changed over cosmic time, the simulations would need to be revised. If the inflation that seeded cosmic structure worked differently than our models predict, if it produced a different spectrum of fluctuations than we assume, the predictions would change. Any of these possibilities could mean structures like Quipu are actually more common or more rare than current simulations suggest. Discovering more structures like Quipu would help reduce this uncertainty. If we find several such structures in our observable universe, we can better estimate how common they are and refine our models. If we find none others, despite extensive searches covering the entire sky to sufficient depth, it would suggest Quipu is genuinely unusual, perhaps requiring us to rethink our understanding of how large structures form. Future surveys will provide this test. The Rubin Observatory will survey the entire visible southern sky repeatedly over a decade, cataloguing billions of galaxies and mapping large-scale structure in unprecedented detail. The Euclid Space Telescope will map a third of the sky from space, unobstructed by Earth's atmosphere. The Nancy Grace Roman Space Telescope will conduct deep surveys over large areas. These surveys will cover more of the sky than current surveys, reach to greater distances, and map structures with greater precision. They will give us a more complete census of large-scale structures, revealing whether Quipu is truly exceptional or merely the first of many such structures to be discovered. With more data, we can better constrain the properties of the universe and the probabilities of rare events. We can test our theories of cosmic structure formation, our models of dark matter and dark energy, our understanding of the early universe. Each new discovery teaches us something about how the universe is organized and how it has evolved from the Big Bang to the present. For now, Quipu stands as a testament to the power of cosmic variance. It is a rare, remarkable structure, a glimpse of what the universe is capable of producing when the conditions are just right. It represents an unusually large fluctuation in the density field of the early universe, amplified by billions of years of gravitational growth into the largest known object in the cosmos. This journey is drawing to a close, and some final thoughts seem appropriate. We started with the scale of a house, a space you could cross on foot in 30 seconds. We have ended with Quipu, a structure measuring 1.4 billion light-years across, holding billions of galaxies and trillions of stars. The ratio between these scales defies comprehension. If you tried to express it as a number, you would write 1 followed by 27 or 28 zeros. It is a number without meaning in everyday life. You have no intuitive grasp of scales this different. Your brain did not evolve to understand them, and yet both are real. Both exist in the same universe, governed by the same physical laws. The atoms forming your home were created in stars that lived and died billions of years ago, in galaxies scattered throughout the cosmic web. Perhaps some of those atoms came from galaxies that are now part of Quipu, enriched in ancient supernovae when the universe was young, scattered into space, drifting through the cosmos for billions of years, before eventually being incorporated into the gas cloud that formed our solar system. The structures we observe through our telescopes, Quipu and its neighbours in the cosmic web, are built from the same fundamental particles as you and me and everything around us. Quarks and electrons, protons and neutrons, the same building blocks arranged in different configurations. The only difference is scale and organisation. This is the deep truth at the heart of cosmology, and everything we have explored tonight. We are not separate from the universe. We are part of it. We emerged from it through billions of years of cosmic and biological evolution. We are made of it, literally constructed from atoms, forged in stellar furnaces and scattered across space. And we possess the ability to understand it, at least partially, through observation, reason, and mathematics. Every atom in your body was forged inside a star. The calcium in your bones was created in a supernova explosion when a massive star reached the end of its life and detonated. The iron in your blood was fused in the core of a dying star. The oxygen you breathe was produced when helium atoms fused together in a red giant star. The carbon that forms the backbone of every molecule in your cells was assembled in the hot interior of an aging star. These atoms have travelled immense distances and existed for billions of years. They have been part of multiple stars, multiple planets, multiple systems. They have drifted through the interstellar medium, been blown across space by stellar winds and supernova shockwaves, been incorporated into gas clouds that collapse to form new stars and planets. They carry within them the entire history of the universe. You are made of star stuff, as Carl Sagan famously said. But more than that, you are made of cosmic web stuff. The atoms in your body have travelled through the filaments and voids of the cosmic web. They have been part of galaxies in different regions of space at different times in cosmic history. They have witnessed, in some abstract sense, the evolution of the universe over billions of years. They have been reprocessed through multiple generations of stars, each cycle adding new elements and redistributing matter across space. The universe is vast beyond easy comprehension, but it is also comprehensible, at least to minds that evolved within it. This is one of the great mysteries of existence, mathematics functions. It describes the behavior of matter and energy with astonishing precision. Physics functions. We can predict the motion of planets, the evolution of stars, the expansion of the universe using equations and theories. We can describe the behavior of matter and energy across scales spanning dozens of orders of magnitude, from subatomic particles to the observable universe. This is extraordinary and not obviously inevitable. There is no clear reason why the universe should be understandable by creatures like us. We evolved to hunt and gather on the African savanna, to recognize faces, to throw spears accurately. We did not evolve to understand quantum mechanics or general relativity, and yet we do. Perhaps this reveals something about the nature of reality. Perhaps the universe is mathematical in some fundamental sense. Perhaps the laws of physics are not just descriptions we impose on nature, but reflect some deeper mathematical structure inherent in existence. If the universe is fundamentally mathematical, then minds capable of mathematics can therefore grasp it, can decode its patterns and predict its behavior. Or perhaps we have simply evolved to excel at recognizing patterns. And the patterns we observe in the cosmos are those our minds are built to detect. Our brains seek order, find regularities, construct models. When we look at the universe, we see patterns because that is what we are designed to see. We might be missing other aspects of reality that our minds are not equipped to perceive or understand. We cannot be certain which interpretation is correct. Both perspectives have merit. This is one more mystery among many, a deep question about the relationship between mind and matter, between observer and observed, between the mathematical structures we use to describe the universe and the universe itself. What we can say with certainty is that the universe is beautiful. It exhibits structure at every scale, from quarks to superclusters. It evolves over time in ways we can predict and comprehend, following mathematical laws that describe its behavior with precision. It contains countless worlds, most of which we will never visit or even observe, each potentially unique, each potentially harboring phenomena we cannot imagine. And it contains us, conscious beings capable of wondering about it all. We are patterns of matter and energy that have become self-aware, that can ask questions about our origins and our place in the cosmos. We are a way for the universe to know itself, to observe itself, to contemplate its own existence. This reflexive loop, the universe understanding itself through us, is perhaps the most profound fact of all. Quipu is the largest known structure in the universe. It is a network of galaxy clusters extending 1.4 billion light-years across space. It required billions of years to form, growing from tiny quantum fluctuations in the first fraction of a second after the Big Bang into the massive structure we observe today. It will persist for billions more years, slowly evolving as galaxies continue to fall along its filaments and clusters continue to accrete mass. It holds more stars than there are grains of sand on Earth. If you gathered every grain of sand from every beach, every desert, every ocean floor on our planet, and counted them, you would not approach the number of stars in Quipu. It contains more worlds than we could visit in 1 trillion lifetimes, even if we could travel at the speed of light. Each of those stars might have planets. Some of those planets might be suitable for life. Some might actually host life, from simple microbes to complex civilizations. And you know about it. You have spent time learning about it, following this journey from human scales to cosmic scales, from your home to the largest structure in the observable universe. That is a small miracle when you consider it carefully. An arrangement of atoms on a small planet orbiting an ordinary star in an ordinary galaxy has become aware of structures spanning a significant portion of the observable universe. Somehow, through billions of years of evolution, collections of atoms have organized themselves into nervous systems capable of consciousness, of thought, of understanding. These nervous systems have developed technology, built telescopes, launched satellites, mapped the cosmos. They have looked across billions of light years and recognized patterns, structures, the cosmic web. The universe is observing itself through your eyes. When you look up at the night sky, when you contemplate the vastness of space and time, when you grasp the structure of the cosmic web and the history of cosmic evolution, the universe is becoming aware of itself. You are not just an observer, you are part of what is being observed, connected to everything else through the laws of physics and the shared history of matter. Every photon that enters your eye began its journey long ago, perhaps from a distant galaxy carrying information across space and time. That photon, a quantum of light, travelled for millions or billions of years, crossing the expanding universe until it happened to reach your eye at precisely this moment. In that instant, information about the distant universe enters your brain, creating awareness of something far beyond your immediate surroundings. This connection is profound. You are not isolated. You are part of a vast, interconnected system spanning the observable universe. The atoms in your body came from stars. The light entering your eyes comes from galaxies. Your thoughts are shaped by patterns you observe in nature. You are embedded in the universe, woven into its fabric. Thank you for joining this journey through the cosmos. We have traveled together from the familiar to the unimaginable, from the scale of everyday life to the largest structures known to exist. We have seen how the universe is organized, how it formed, how it has evolved over cosmic time. We have glimpsed our place in this vast cosmos, neither at the center nor at the edge, but somewhere in between, observers capable of understanding what we observe. Sleep well tonight, knowing that you are part of something immensely larger than yourself. The atoms in your body are billions of years old, forged in stars that lived and died long before Earth existed. The light you see from distant stars began its journey before humans existed. The structure of the universe extends far beyond what you can see or comprehend, yet you have grasped a piece of it tonight. And may you never stop wondering about the universe that created you. May you continue to look up at the night sky with curiosity and awe. May you remember that every atom in your body is a piece of the cosmos, that you are quite literally made of star stuff, connected to everything else through the cosmic web of matter and energy. May you appreciate the improbable miracle of your existence, the unlikely chain of events that led from the Big Bang to this moment of consciousness contemplating its own origins. The universe is large beyond imagination, old beyond comprehension, beautiful beyond description, and you are part of it. You always have been, and you always will be. Every breath you take connects you to the cosmic cycle of matter. Every thought you think is the universe thinking about itself. You are a temporary pattern in the eternal flow of energy and matter, but a pattern capable of wonder, of understanding, of love, that makes you extraordinary. That makes your existence precious and meaningful despite the vastness of space and time. Sleep well and never stop wondering.